Hi class, welcome to the next section in chapter 13. This is 13.9. We will be talking about power series representations of functions. So, just like the name says, we're going to look at how a series um, can behave just like any other function. Okay. So we saw in the last video that these power series are basically polynomials. We discussed a little bit about how these polynomials can be made to approximate a function either over an interval or everywhere. Okay, and I keep saying approximating, but really we're talking about equality here. Okay, the approximations kind of come outwards, so we'll talk about that a lot more in the next section. In this section, we'll again work on some of the intermediary uh, basics into that sort of discussion. So let's consider a power series. So our coefficients are all 1. We're starting at 0. We're going to infinity. Here, that we're looking inside of an interval between 1 and -1. The one's not included. So our x value here is less than 1. Um, remember that this is pretty much the same thing as a geometric series. Okay. If we write this out term by term, we have 1 plus x squared plus x cubed and so forth. And this converges whenever this value of x is within 1 and -1, okay, absolute value wise, right? So it represents a geometric series. So by inspection, let's say that we had x was 1/2. That's less than 1, right? So this should be a convergent geometric series. If we write this out term by term, again, this is a geometric series, right? So 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, so forth and so forth. We just keep doubling everything, right? So we know that the sum of the geometric series is calculated by our value of a divided by 1 minus r. In this case, r is the 1/2, and that a is that first term 1. Okay. So if instead of using 1/2, we're saying that x is any value within 1 and -1. Okay, so within this interval, we replace r with x. So instead of using 1/2, we're going to replace this with x. So we're really just using this as a pinpoint example for what this looks like. Okay, our a value would still be 1 in that case, right? And our sum is going to be 1 over 1 minus x, this x being in between 1 and -1. Well, this is a function, right? So this function, 1 over 1 minus x, is equal to the series 1 plus x squared plus x cubed, so forth and so forth and so forth. So this function has a series representation, okay, a power series representation. So the power series about x equals 0, right, because my radius is centered at 0 here, the radius of 1, has this general form, okay? So I can write this up, right? I can say that 1 over 1 over x is equal to this series instead of writing it term by term. I can just say that this is a series representation whenever the absolute value of x is less than 1. So let's say we wanted to find the power series for a function that's very similar to the function that we just derived, this 1 over 1 minus x. This is our starting point. Well, how would we go from this to something slightly different, right? And that's basically what we're going to do in this section is we're going to look at how we have something given to us and how can we change that so that it matches the function that we want it to match, right? So the difference between 1 over 1 minus x squared and 1 over 1 minus x is I have an x squared instead, okay? So then my series, instead of being just x to the n, I would substitute for x squared, right? And so when I write this out term by term, 1 plus x squared plus x to the fourth, x to the sixth, x to the eighth, x to the 10th, etc., right? And this is going to converge whenever the absolute value of x squared is less than 1, right? So I'm really just substituting in my change into all of the pieces I had for the previous series, okay? So my interval of convergence is the same. It's still from -1 to 1. So at the endpoints, I would still diverge. One thing to note here is that even though our substitution of x squared into our power function gives us the same interval of convergence as the original. That's not always the case, right? So let's say I had like x squared plus 1. I would have a different interval of convergence, obviously, right? I would have to uh, subtract the 1 over here, or plus 1, whatever it is I'm adding in, and that's going to change the value here for this radius, okay? So just because in this case I came out with the same radius does not mean that's always the case, right? You have to work it through all the way each time. So if I'm substituting into a power function, I have to reevaluate my interval of convergence, right? So let's do an example. Okay, so let's express 1 over 3 plus x as a series. So we're going to do the same thing. We're going to take the series that we know information about already, and we're going to try to manipulate it in order to look like this. So last time our change was that we had an x squared. So what do we have different here, right? So recall we have 1 over 1 minus x is our previous equivalency, right? Power series representation. So the difference here is that I have a 3 instead of a 1. And instead of a minus x, I have a plus x. So I am going to have to plug something in for my x, and I am going to have a change here somehow in order to deal with this. So what I want is I want my function to get basically into the same form that I have here and just make an appropriate substitution when possible. Okay. So the form of our function is very close to the form of the power series that we already know, as I said, right? So we have to make an equivalent adjustment. So when I say equivalent adjustment, it means I'm going to be manipulating this expression here, but maintaining equivalency. I can't just like add something here and divide something here. If I multiply by something, it's got to be numerator denominator, right? I can factor something out, right? I can anything that if I add something, I got to subtract it away as well, right? So I can't change the value of this expression. I just want to change the way it looks. So we'll be algebraically manipulating it into a form where I can do some sort of substitution like I did here. Okay. So here I have 1 over 3 plus x, the form that I have. There's actually a couple things that we can do. So the first is let's separate this 3 into 1 plus something, right? Now this looks a little bit more like what I need, except that this plus is kind of messing me up because I need a 1 minus x, right? So if I can have this as 1 over 1 minus something here that I can use to substitute in, that's kind of what I'm looking for. Okay, so let's try to play around with some signs here to see if we can get a 1 minus something. So if I subtract a subtraction, it turns into addition. So I'm pretty good here. So now I have 1 over 1 minus a negative of 2 plus x. Okay. I can go ahead and distribute this negative if I want, but this actually might be easier for me to deal with. Okay. It's really up to me at that point. Now, remember when we have a negative here to an nth power, it's a lot easier if I just pull this out into an alternating series. Okay. So I have negative 1 and then this 2 plus x to the nth power, right? So this is still a power series, okay? Everywhere I see x, I'm going to replace it with 2 plus x, and I'm going to alternate the signs, right? So that's the change that will be happening to this. So everywhere I see x, I'm going to replace it with 2 plus x, and I'm going to alternate my signs, all right? Now, this is going to converge when 2 plus x is less than 1, right? Because then it'll be geometric in nature. And I don't care if a geometric series alternates or not, it's still going to have the same sort of convergence. And so I'm going to have 2 plus x is less than 1 is my requirement, okay? And so I can split this across so that I can find my actual interval, right? So then my interval is then going to be negative 3 plus 3, right? Because I'm going to add 2 over here. I'm still centered at 0. And so um, that is what I'll have. So equivalently, we could have done this another way, right? So I have 1 over 3 plus x as the function I'm interested in. I could have just pulled out a factor of 3 from each piece, and now I have 1 over 1 plus 1/3 x with this multiple of 3 on the outside, and then did the same kind of shifting that I did before, right? So I'm taking this plus and I'm turning it into two negatives. One's attached to what I'm plugging in. The other is helping me to maintain the form that I needed. And then this 1/3 I'm pulling out as a constant multiple, right? So then my series looks like this, 1/3. Um, and then the general term is negative 1/3 x to the n. Obviously, this negative I can replace with an alternating form, okay? Negative 1 to the n on the top. Here I have 3 to the n. I have one more 3 on the outside everywhere, so I can multiply that back in, and that'll just give me n plus 1, which cleans it up pretty nicely here. And then I just do the same thing that I did before, right? So my constant term is this 3n plus 1, so I really just need the 3 x, okay? And then that gives me x is less than or equal to 3, absolute value-wise, without the equal sign. So this is going to converge over this interval of -3 to 3. Again, we'd have to check the endpoints to get the exact interval, but I know for certain that between -3 and 3, endpoints not included, that it converges, right? So this is going to match with our power series representation that we had before, right? So here with this other calculation, I got -3 and 3 when I did it this way. And to no surprise, I get the same answer when I pulled out a 3 instead, because this interval isn't going to change, right? So if I do it a different way and I get a different answer, one of the ways I messed up somewhere, right? So my answers have to agree because there's only one interval for the series. So let's look at another theorem. If I have a power series that is centered at A, and this power series has a radius of convergence of r, which is larger than 0. So remember, when it's equal to 0, it's only at a exactly that it converges. Um, so here I need some sort of an interval. Then the function f that is defined by this power series representation centered at a, okay, can be written in this form, right? So I have my coefficients centered at a, and my powers for x continue to increase. This is going to be differentiable, which makes sense because this power series representation is a polynomial, right? And since it's differentiable, that means it's continuous, right? And it's going to be differentiable and continuous on this interval centered at a of a radius of r. So I'm going to subtract r from a and I'll add r to a, and that will be the interval, okay? The derivative of my function is just me differentiating this polynomial power representation term by term, right? So C naught goes away. Um, this, using the chain rule, right? This is always just going to be x, okay? And then times C1, right? So then this disappears and I get just the constant. Here I'm going to get 2C2x minus a. Here I'll get 3c3x minus a squared, okay, and so forth. So term by term, I'm just differentiating. Okay. So that is the derivative of my function, represented as a power series. So here, I can also take the derivative of the entire series term. The n is what drops down, ncn, and n reduces by a power of 1. Okay. So this is the general form for the derivative of a power series. The integral is the same thing. I integrate term by term. So this turns into C naught x, okay, plus the constant of integration. Can't forget that. So we get C naught times our x minus a. This one turns into 1/2 C1 x minus a squared, okay, 1/3 C2 x minus a cubed, and so forth and so forth. Okay. So again, that's our term by term. And we can write the general term by just integrating the general term here. Okay, so constant of integration, and then me integrating that general form for the power series. All right, let's do an example. So this is powerful because now we can not only represent a function, but we can differentiate and integrate difficult functions by looking at the power series representation. So let's find a closed form for the sum n times n minus 1 x to the n minus 2. Here, notice we're starting at 2. Um, Notice that when we differentiate, we start at 1. Okay, so notice that when we change these things, because the C naught term goes away when we differentiate, we start off with C1. So our n has to start off at C1. Okay, find a closed form for the sum. So if we write these terms out, um, it's 2 plus 6x plus 12x squared plus 20x cubed, so forth and so forth. Okay. So we have the series representation, but what about a function representation? That's what it means by find a closed form. Find the function that is this series here, right? So note that if I integrate this function twice, notice I didn't put the dx's. That's just because this is an informal double integration. I'm not necessarily saying like, hey, look. So if I integrate this twice, okay, I am going to get back to the power function, okay, at n equals 2. And that's because when I integrate, the bounds, the starting place doesn't change, okay? So if I integrate this twice, um, I'm going to get x to the n, okay? Obviously, there's two different constants of integration as well that comes with this. Um, so we can deal with that. But informally, I get x squared, x cubed, x fourth, et cetera, right? You can do this on your own if you want to double check this, but it should be pretty clear that this is a second derivative, right? If this is a power series and this is the first derivative, if I differentiate this again, I get n times n minus 1, dropping down cn x minus a. This turns into n minus 2, which is exactly what my example is, except I'm centered at 0, right? So if you didn't catch that previously, that's what this is. So it's very obvious that if I integrate this twice, I get back to the power series, okay? So it's like this. So I have x squared plus x cubed, x fourth. So this differs from what I started with, or what I know of 1 over 1 minus x. But just looking at this, it's very clear that this is a geometric series, okay, where r starting off with x and a is x squared. All right, so the first term is x squared, and then I have a times x, so x squared times x, and then so forth and so forth and so forth. So I'm able to pull out my form so I can plug it into the summation for series. So a over 1 minus r is the sum of this series. So this is the function, right? This is the closed form of the function of this power series, x squared over 1 minus x. If I differentiate this twice, okay, I'm going to get the following. So this is me differentiating once, okay? Again, so you might say, why would I differentiate? So we didn't actually finish finding the answer, right? I took a general form, right, in order to get some sort of a general idea of what this will look like. But I need these to actually match up. So I'm going to take my result here that I differentiated, that I integrated twice, and I'm going to differentiate it twice to bring it back to try to match things together, okay? So first derivative, I'm using the quotient rule. So I get x squared turns into 2x. I multiply times the bottom function. I subtract from that this derivative times this function, and then I square this on the bottom. Okay. If I simplify this, multiply everything out on the numerator, I get to cancel things out a little bit, and I can factor, right? So this is just a negative x squared because there is negative 2 and a positive 1. I can pull out an x here. Okay. So I have x over times 2 minus x, 1 minus x squared. That's the first derivative. Okay. I could have kept it like here. This might be easier to do a second quotient rule, but it doesn't really matter. So let's do the quotient rule one more time. So that's y prime. I'm going to do the quotient rule once again. Maybe do this on your own and check your answer with what I have here. Let's see if we come up with the same thing. But I'm going to get this for differentiating this. So this turns into the power rule times this function. Here, I really just differentiated that. It's much easier to do that. minus the denominator uh, being differentiated times the numerator. So it was easier to look here. And then this gets squared, so I have now 1 minus x to the fourth. Okay, I want to simplify this. I'll multiply stuff out, try to cancel things where I can. Here you see I have a 1 minus x that cancels, a 1 minus x, and a 1 minus x. So I can at least cancel one of these on each of these terms. Um, here, so I did cancel. Here I factored a 2 and I brought it in to the 3. Okay, here I factored out a 2x. Okay, or just an x, I'm sorry. And so I can cancel one. So this drops down to a 2. This one cancels. This one drops down to a 3. This is what I'm left over with. Nothing else cancels, so I can start to multiply things in so that I can add and combine like terms, right? So I have 2. Um, well, first I had to square this, right? So I get x squared minus 2x plus 1, and then I distribute that 2 across into that, and then this just multiplies out. So you got the 4x minus 2x squared. This is here. Things cancel. I have a negative 4x, a positive 4x, a negative 2x squared, a positive 2x squared. So I'm left with just 2, and the denominator is 1 minus x cubed. So this is the actual closed form function for this series. Okay, so that's my y double prime. And so this sequence, this series, I'm sorry, is the power series representation of this function. Okay. So again, what did I do? I recognized this general form as the second derivative of the general term of the sequence. So I integrated it twice. Okay. So I know that this is what I get when I integrate it twice. I noticed it was geometric in form. So I found the sum of the series, right? I got this. But remember, this isn't what I was looking for. Okay. This isn't my series. This is my series, not this. So how do I go from this to that? Well, I differentiated twice, right? So I had to be tricky, right? So now that I came back up here, I undo what I just did and I differentiated twice. Boom, 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 and I got an answer. And that answer then is equal to this. So I have now my power series representation for this function. Okay. Next example. Find the series expansion for natural log of 1 plus x divided by 1 minus x. Okay, so this is the input for the natural log. Let's go ahead and, so I want to find the series expansion. This series here, this function, doesn't really look anything like what I know so far, right? So from previous work, okay, I figured out the power series representation of 1 over 1 minus x. I figured out the power series representation for 1 over 1 minus x squared, for 1 over 3 plus x, and I was even given some general series, and then I found its series representation, right? Which was, so this general form, boom, was this function. But none of these look like natural log with a bunch of stuff in that, right? So this is very convoluted in form. So the only thing I know about this is that natural log has its own rules. So let's go ahead and apply the rules of natural log. So I can go ahead and separate this. I have natural log of 1 plus x minus natural log of 1 minus x. If I differentiate these, then I will have, right, I can separate the natural log inside of the differential. So differentiating one side is the same as differentiating the other. And I know that when I differentiate natural log, I get 1 over whatever is inside of natural log. So now I have 1 over 1 plus x plus 1 over 1 minus x, which is very, very similar in form to the things that I already know. One of these we already have the power series representation for. The other one we have to replace negative x everywhere we have x. Okay. So for one, I have negative x, which is going to give me an alternating series. okay, plus the one that I know already. And so now I have an alternating form plus the power series representation for 1 over 1 minus x. And so if I integrate both of these, because remember, I had to differentiate in order to get this form. And so now that I know what that form looks like, I have to integrate to undo that differentiation to bring it back to my original problem. Okay. So writing these down, okay, term by term, and differentiate, or I'm sorry, integrating term by term. So again, I can just add these all together first, which is probably the easier thing to do rather than this whole thing term by term and this whole thing term by term. So notice that every other term disappears. The negative x and the x will cancel. The negative x cubed and the x cubed will cancel. X to the fifth, the x to the seventh, the x to the ninth, all of the odd powered terms will cancel out. Okay. And the evens will add together. This is why we get these twos. Okay. So I have 1 plus 1, x squared and then x squared, x fourth and then x fourth, etc. Okay. So when I integrate this, I can pull out the 2, integrate term by term. This will be x, 1/3 x cubed, 1/5 x fifth, 1/7 x seventh, etc., etc. Okay. Plus that constant of integration. So writing this in a general form, uh, my coefficients are given by 1 over 2n plus 1. They're all odds. They're all in the denominator. Okay. Starting at 0, I just need to make this so that the beginning denominator is 0 also, or I'm sorry, 1 also, and then counts up by 2 each time. So this works for that. And then the powers are going to match the denominator, right? 3 and 3, 5 and 5, 7, 7. So this denominator and this denominator, right? So just to recap, I took my natural log, I split it using the properties of logs. I differentiated because that got me to a form that I can work with. Once I had the general form of those forms, I had to go back to my original function by integrating. So before I integrated, I combined everything term by term, and then I integrated everything, and then I found the general term. So this general term is equal to my function, natural log of 1 plus x divided by 1 minus x. Okay. So note that if I plug in 0 to my function, again, I plug in 0 here, I get 1 over 1. So natural log of 1. Natural log of 1 is 0. Okay. If I plug in 1 for, I'm sorry, 0 for my function, okay, this whole thing goes away and I'm left with c, right? So natural log of 1 over 1, natural log of 1 is 0. So if I plug in 0 here, this whole series goes away, but c is still constant. And so since when I plug in 0, my function has to equal 0, that means that that constant has to be 0 as well. Okay. So c is equal to 0. Since my series is equal to 0 at the value of 0 for x, um, the absolute value of x has to be less than 1. Okay. For our radius of so our radius of convergence is then 1, right? Since my value of x, there's nothing being added to it, there's nothing being multiplied to it, right? This isn't a constant term. This is what the coefficients are given by. So as far as the x goes, anything that has to apply to 2 does not get included. X itself just has to be less than 1. So that is geometric in form and converges. Okay. Looking at the endpoints, right? We should always be checking our endpoints. If I check 1, I'm going to have the series 2 over 2n plus 1. This is just going to be 1, so that whole thing goes away. So what does this do? Well, we'd have to check, right? It's not geometric. It looks kind of harmonic in nature, so it probably diverges would be my guess. So using the limit comparison test with the harmonic series, we take the limit, numerator and denominator. Denominator is 1 over n, right? Um, multiply by the reciprocal, okay? And we have 2n on top. The n's are what drive everything as n gets large, so the coefficient here is just 1, which is not 0, okay? Larger than 0, so it's divergent. So since it's larger than 0, it doesn't go to 0. it does whatever our comparison does. Comparison diverges, harmonic series diverges, so our series diverges. So I'm divergent at x equals 1. I gotta do the same thing for x equals -1, and I'm gonna get similar results. Okay. But remember, when we plug in stuff, we gotta check our bounds. So my interval of convergence for that example is -1, 1. All right. So there's a little bit of everything. I will see you guys on the next video.